Okay, good morning, everybody. I think we will begin. Um, Good morning and welcome to this webinar. This webinar is brought to you by Paratus through the Disaster Risk Stakeholder Hub. My name is Ben Hall. I'm from the Resilience Advisors Network and I'm one of the facilitators on the CMIND platform, which is hopefully where you registered for this webinar today. I'm delighted to be your moderator, and we're joined by members from the MYRIAD, MIRACA, C2IMPRESS and MEDiate projects who will introduce themselves to you shortly. We're thrilled that so many of you could join us today. So today's topic, and the reason you're all here, not to listen to me, is multi-hazard risk assessment, concepts, tools and applications. So before we dive into the webinar itself, I'd just like to mention a few housekeeping rules if you don't mind. So this session is being recorded and you'll be able to access the recording later on the Disaster Risk Stakeholder Hub. That will be uploaded there by this evening and you will get an email notification to say so. So please share it between your colleagues. If I could ask that when you're not asking questions, please keep your microphones off during the webinar. We encourage you to keep your cameras on to enhance engagement, but that of course is entirely up to you. Our webinar today is scheduled for 1 hour and 30 minutes. However, the last roughly 30 minutes is a panel discussion and question and answer session. So if we fall slightly short of that time, then you will get some time back and we will end the webinar 10 minutes early. If you've got any questions throughout the webinar, could I please ask that you write them in the chat and we will address them during the question and answer session towards the end. And here is a real brief agenda, so I won't read it all out to you, but I'll leave it up on your screen for 30 seconds or so, just so that you can have a quick look through it. So you'll see we've got an overview of the projects at the beginning, before moving on to the projects presenting some of their work, and then moving on to the panel discussion. And I'm just going to take 2 more minutes of your time before handing you over, just to give you a real quick introduction to the Disaster Risk Stakeholder Hub. So hopefully you've visited it before. It's available on the QR code that appears throughout the webinar, as well as the website there, DRS-hub-EU, or through the CMIND platform. It's designed as an entry-level reference point for anyone involved in disaster risk management. So not only the projects that are involved in it, it's meant for citizens, local organisation, responders and municipal or regional authorities, national and international bodies, and researchers and policy makers. Originally, the hub stemmed from the Paratus project, which engaged stakeholders across Bucharest, Caribbean, Istanbul, and the Brenner Corridor. It recognised the need for a universal platform, and its scope has since extended. So some of the key features that the hub include, and please feel free to go on and give these a go, is it's got baseline knowledge and tools. So the hub offers a wealth of information, including terminology, disaster databases, vulnerability and loss and damage data, as well as reduction measures and best practices. It's got simulation engines, so it features interactive tools such as impact chain generators, hazard assessment tools, risk assessment and reduction tools, and serious gaming, as you may have learned about on the last webinar if you were here. It's got an area for community engagement, so it's got an interactive members forum and scheduled events such as this webinar, conferences and expeditions. It's got an intelligent search function, so one of the most exciting bits is got a structured and AI-driven search facility that makes it easy to navigate through the extensive disaster data sets and knowledge bases. And where this really comes into its own is it is designed for any of the stakeholders to be able to use. So if you were a teacher, for example, you could search it, or if you were a firefighter, you could search it, and it will give you relevant information for your role and what you do and who you're looking to protect. It enables greater project longevity and relevance, so it preserves valuable outputs from research and innovation projects. And it is a central access point for all stakeholders. So it functions as a unified gateway where diverse groups, from local government officials and educators so researchers and policymakers can effortlessly access critical data, tools and resources. And the final point in there is the opportunity for projects to store resources, share findings and enhance engagement. So it gives a dedicated platform for archiving project resources. The hub facilitates a seamless sharing of research outcomes, best practices and innovation tools. It's a centralized repository, not only to preserve knowledge, but also encourages active dialogue and collaborative engagement. And the last slide before I hand over to the projects then is really just talking about how we're going from project level to a cluster-based approach. It's an exciting evolution in our collaborative efforts. So by uniting 15 projects under the Societal Resilience Cluster, which is hosted by CMIND, we're not only sharing diverse methodologies, key findings and research outcomes, but we're fostering an environment where innovation thrives through cross-project learning. The initiative allows us to pool our expertise and resources, ensuring that the strength of each project contribute to a more comprehensive and effective approach to disaster risk management. It enhances our stakeholder network by bringing together different sectors, ensuring that voices are heard from local communities to national bodies. And additionally, each of these webinars is designed to adapt its format based on the topic being discussed. This means whether we're delving into technical methodologies or sharing success stories, we can tailor our sessions to best address the subject matter. Overall, the cluster-based approach is not only increasing our collective impact, but it also lays the foundation for long-term sustainability and continuous knowledge exchange amongst participants. Thank you for giving me your time there. I'm now going to hand you over to the projects to introduce themselves and the real reason that you are here. So MEDiate, I will hand over to you, please.
Yeah, thank you, Ben. So, hello everyone, we are MEDiate. MEDiate Project stands for Multi-Hazard and Risk-Informed System for Enhanced Local and Regional Disaster Risk Management. You can follow us through the project link and a project website, LinkedIn, etc. But in the project, the ultimate goal is to integrate multi-hazard risk governance framework and community-centered resilience and decision-making. And this has been achieved in the project through the consortium as shown on the bigger map. We have 18 partners organizations from Norway, Netherlands, Austria, France, Italy, Iceland, and the United Kingdom. We didn't stop at the research achievement, but we try to work on the policy. So with policy on integrated multi-hazard risk governance framework, we want to establish institutional and legal frameworks that mandate holistic risk assessment and multi-hazard preparedness across all levels of government. This policy will help to account for the challenges of increasing frequency and interaction of hazards, and which demands integrated planning going beyond the conventional method of treating each natural hazard like floods, earthquakes, and wildfires as separate and isolated events. And the policy on community-centered resilience and decision-making, we want to embed participatory and inclusive risk management practice into disaster policy at the local and regional levels. The MEDiate Project emphasizes people-centered, service-oriented approaches. We are interested in a policy that can reflect this by enabling local actors to shape and implement the resilient solutions. Thank you all. Please explore our webpage. Thank you.
That's great. Thank you, Chen. Rui, I'm going to hand over to you for C2IMPRESS, if you don't mind, sir.
Hello everyone, good morning. I'm Rui A, Perdigão, physics professor and also head of the Meteoceanics Institute, contributing to C2IMPRESS. C2IMPRESS, like the brothers and sisters projects here, is a very interesting project that seeks not only to advance knowledge, so to know what is happening in terms of hazards and multi-hazards, how they interact, and to advance the science, but also to understand, which means to describe not only what, how, but also why things happen, how they interact, and going from fundamental development of methodologies to assess the whole hazard risk cycle to designing policies as well, and governance structures, and dealing in its interplay between frontier natural, social, and technical sciences, and from the lab to the field and to the stakeholders, all co-creating knowledge, advancing the understanding, and trying to find solutions to work for the better of us all. We have a beautiful consortium with partners from all over Europe, and we are going to discuss some of these more details afterwards. All in all, essentially a system of systems perspective, where you have many different systems, natural, social, and technical, working together for a better world. Thank you very much. Let's move on.
Thank you, Rui. That's brilliant. Raghav, I will go over to you to introduce MIRACA, please.
Yeah, thank you very much. So I am Raghav Pant, a Senior Research Associate at Oxford University, and I'm representing MIRACA on behalf of my colleagues. So MIRACA is called Multi-Hazard Infrastructure Risk Assessment for Climate Adaptation. It is a consortium of partners from led by partners at IBM Amsterdam, and including us at Oxford. It has colleagues from Thessaloniki in Greece, University of Ljubljana, Deltares, and Virtuality and Lobelia, which were companies based in Spain. The project essentially looks at infrastructure networks of transport, energy, telecom, schools, and hospitals. And the key underlying questions of the project are: how can we quantify infrastructure risk, climate risks, mainly capturing direct and indirect impacts, because this is something that's not very well understood. And in order to kind of build all this knowledge, we are kind of building models and tools at the pan-European level. And we also have specific use cases as shown in this map, specifically for countries such as Spain, Netherlands, Greece, and Slovenia. And using all this kind of information and knowledge that we create, we want to understand and answer the fundamental question of how do we prioritize infrastructure climate adaptation. Essentially, how do we invest, where do we invest, and which infrastructure networks do we prioritize given the limited budgets and the funds. So looking forward to talk about this more in later in the session today. But yeah, you can kind of, this is a very exciting project, and we are excited to be part of this collaboration with other people as well. Thank you.
Raghav, that's great. Thank you very much. And Philip, over to you, please.
Very much. So finally, I introduce the MYRIAD-EU project. My name is Philip Ward. I'm a professor of multi-hazard risk at the Free University in Amsterdam. And we are leading this project in Amsterdam. It's a consortium of 20 different organizations, from research to industry to policy, NGOs, and so forth. And the idea of MYRIAD is twofold. Firstly, we also want to develop these tools, methodologies, understanding of multi-hazard risk and how all of these hazards interact to cause risk. But also we have a large focus on how can we actually better manage those risks by taking this multi-hazard, multi-risk approach. And that's why here you see these 5 pilot regions, which are at the heart of our project: the North Sea, Scandinavia, Danube, Veneto, Canary Islands. And in each of these regions, we've been working together over the last 4 years to try to come up with risk and adaptation pathways towards the future that consider these interactions between these different hazards. So very much looking forward to discussing the project and the other projects today.
That's great. Thanks very much, Philip. Rui, right, we're going to hand back over to you, please, sir, to talk us through the multi-hazard intelligence key concepts.
Thank you very much. So we can move on to the first slide. So next. So essentially, in terms of multi-hazard concepts, so it's a delicate topic because we hear a lot in our communities when we sit with stakeholders, with end users, and it's quite often also in the academic setting that multi-hazards are often perceived as the existence of multiple hazards, and this is part of it. So you have multiplicity. You have many different hazards happening. However, it's like with complex systems. What makes a system complex is not the number of variables involved, not the number, in the case of hazards involved, but how they are interacting. So even if you have just 2 or 3 elements, the way they feed back into each other, reinforcing or mitigating, depending on what happens, is what brings the complexity upwards. So you have essentially 3 big families of multi-hazards, 2 very well known. So when the cascading, hazard 1, causes 2, causes 3, causes 4. For instance, you have a big anomaly in thermodynamics in the middle of the Atlantic Ocean, and then afterwards it triggers fluctuations in the North Atlantic Oscillation, which in the atmosphere, which will then trigger fluctuations in weather regimes that then will condition the occurrence of, for instance, heat waves or cold waves and drought periods, flooding events. So you have this kind of cascading, which is very well known. Then you have the compound, where you have essentially the conjunction or the synergistic effect, where you have different things happening together in space and time. So essentially collocated, that together compound to yield an impact. For instance, you have, so imagine you have a big earthquake, and then you have also, so you have a dam break, you have a bit of a cascade there as well. But if you have rain on snow, if you have fire and wind together happening, so these kinds of hazards, when they interact together in space and time, in the joint event, as you have across the projects, so we will see later that different projects have these features, then the compound effect can be even higher than if each of these hazards would be taking place separately. But then we have this nonlinear interplay. In complex system science, it's a very hot topic of how the different hazards interact, meaning that, you know, the effect can feed back into the cause, reinforcing it or mitigating it. And that happens a lot. For instance, you know, in a forest fire, let's say that you have a dry periods that will facilitate initial propagation of a fire event. You have a lot of biomass, everything had been drying up, you have a bit of wind due to some, you know, to an atmospheric circulation regime. And then, okay, once you start having that event and once the fire acquires a certain dimension, it will create its own low pressure pocket, and then you'll start having convection, and that convection will trigger even more winds, and it will even, in many cases, reverse the winds. For instance, you have a high pressure over a certain area, and then you create a low pressure with a fire, and then it will trigger inversion of the winds, and when everybody's following the Met Office directions about the wind and fire propagation, it's all inverting. So this is something that in Portugal killed many people in 2017, and in 22 it also gave a lot of trouble. So this is an interactive multi-hazard where instead of just a cascade or a compound, you have a reversal of the causal chain. So next, please. So you can move to next. Okay, so in order to assess this situation, a lot of methodologies are needed in complex system science. So one of the first things, when you look at events, when you look at spatial temporal occurrences, when you look at the data, and when you look also at the dynamic models that deal with the different hazards, you see in emergency systems, now you have it all siloed into different departments where you have expertise in different areas, but we need to bring them together. And that is what the different projects aim to do, which entails then taking the data pertaining to some kind of mumbo jumbo of different events happening all together. Like, for instance, the first picture, nonlinearly entangled system signatures. Imagine you have all these processes and interactions happening. How do you disentangle that? If they would be linearly combined, which would not be a real multi-hazard, then you would just factor it out. You get some machine learning algorithm and it decomposes the matrix and then you would separate the event. However, that is not what happens in natural science, in natural worlds, because you have this nonlinear interplay, you have these feedbacks, you have something that is mixed in a way that is irreversible. And if it's a reversible mixing, you cannot use the typical AI and machine learning techniques to disentangle. You need to use nonlinear science. So this is where we come in. To disentangle the processes that are underlying these complex interactions. And then you see that a lot happening between ocean, atmospheric, geophysical in general, and also very crucially in the socio-environmental dynamics, how we managed our lands, how we respond to the events, how society is acting, both at an event scale and at the long-term planning scale. So when we do simulations for long-term hazard systems, we need to take into account this behavioral of dynamics of the socio-environmental system. And then in the rightmost panel, in the rightmost panel, then you see, for instance, here you have the floods and droughts conjunction happenings emerging from a synergistic effect among different ocean atmospheric circulation regimes that then individually do not trigger anything, but in a combined manner, they trigger that multi-hazard. Next, please. Okay, so just as a brief note here, so the secret here, and that is something that permeates across the different projects, is looking at multi-hazards and also at the governance of them and the management and the adaptation, the measures that you take from them, not from just a conversational approach, but from a complex system science approach. Of course, I'm a suspect here because I'm a professor of complex system science, but we work closely with experts of multi-hazards to jointly develop this. And I've been doing that for almost 20 years. So because our planet is a complex dynamical system, everything is interacting with everything. Nature, society, technology, our built infrastructure is very important. How can I make a climate projection for 100 years if I don't know what is going to be happening in terms of building, in terms of channeling, in terms of adapting our terrain and our oceans and our atmosphere and even space, even the presence of the material in space. So complexity is then crucial to encapsulate the rules, the modeling, and also the conversations on the table, that everything is deeply connected, as everybody knows and everybody feels. Next, please. So, yeah. Okay, so underlying, just leave it this here, you will have access to the papers, to the materials. The underlying that is essentially hard science, so meaning that rather than just seeing this from a purely data-based approach where you analyze some data and you infer some models that can be geometric, dynamical systems, can be information theoretical, can be, so anything that is just purely data-based, no, you need to be process-based, understanding. In this regard, it's not just physically informed machine learning where you put some physical rules conditioning the learning approach of handling the data, but also understanding that the learning process is not purely statistical, is not purely analytical. It is something that is inherently physical in the sense that our learning approaches to dealing with multi-hazard information for planning and for early warning detection and modeling simulation and relaying that information needs to be coming from an information physical approach, which means understanding rather than just knowing, understanding the whys rather than just describing, and essentially finding the patterns, the symmetries, and the symmetry breaks in the emerging world of challenges that we are facing these days. And if you just see what is in the data, you just see the recurrent patterns. That is not helpful. If you look into this kind of science, then you can see beyond the data and can see emerging behavior, even those that have not manifested in the data, which is crucial for emerging multi-hazards. Next, please. Let's see whether I can finish this on time. Yeah, so when it comes to practice, down to the field, because we are also on the field, we have to be there, we work also on the field, is this integrated approach from academia to the field, from the lab to the terrain of operations. So bottom-up synergy from cooperating stakeholders sitting together with public-private citizen partnerships, like we have in one of the projects. And then also the top-down governance. We have rules that apply to the society as a whole. And then this interplay from sensing, all civil protection mindset, in which you go, you sense what is happening, you diagnose, you make early warning signatures, you use citizens as sensors. They detect what is happening, they feel what is happening. You have sensors from space, from the ground, from the field, mechanical sensors, electromagnetic, gravitational, and people with their knowledge that assess situations that we in physics can't. And then all of this comes together. We are mixing all of that together into interdisciplinary models. It's not just numbers, it's not just letters, but it is something that blends natural, social, quantitative, qualitative information in a rigorous manner. Categorical algebra helps to do that. And then you have the action. As Philip was mentioning earlier, yeah, we need to do something. We need to manage the risk. In the pilot use cases that you see in every project, and also in the broader society, in the broader Europe, with tools that work not only in place A, B, C, D, but everywhere. So, of course, you have specificities in the local places, but the core principles, they permeate across all of us. And it is fundamental to have this coevolution between what we see, what we do together, and how we act to help the people. But listening to those at the bottom that are the foundation of our society, all of us as citizens and farmers, and the top down, how we encapsulate this into rules that everybody should then be able to work with in a coherent, cohesive, sustainable society. Next, please. I'm almost finishing. To put this together, the mathematical formulation to deal with all of this is essentially a system of systems intelligence. What does it mean? So we create a system where you have the multiple participating areas of science and technology. So you combine data science, you combine physical science, social science, environmental science, the various areas into a coherent system dynamic framework that admits the different formulations, the different languages. So this is a language of languages. It's more than natural language. It's more than mathematical language. It's a system of systems of different languages that articulates, it's kind of a Babel tower, where you articulate the different languages to simulate and to help the people work together towards a better world. Next, please. Yeah. To finish it, the next. Okay, and just now as a final note, so this is not just something academic, abstract, and magical. No, it's something that needs to work on the field, providing anticipatory information. Like in this panel here, you see predicting 30 weeks in advance the emergence of atmospheric rivers that won't be attacking my home country, Portugal, where you look at weather data and then you see that much later. So early warning signs, also agricultural risk. You look and feel well in advance, not just from sensors from space, but also from the knowledge of the field, of the farmers, that you see risk happening, emerging into the agro systems, and also our quantum aerospace system dynamics of capturing from space with novel sensor techniques, emerging signatures of multi-hazard risk dynamics way ahead of time. And this is very important across all the projects to see what is invisible and to predict what is unpredictable across multiple sectors of activity, from the lab to the field, from the most theoretical to the most applied, because we all have to sit together and get it going. And everybody in this room is doing that. And I thank you all for your great service. Thank you very much, and let's move on.
Rui, thank you very much. That was all really interesting. If you have any questions on what's just been discussed, please put them in the chat and we will come to them in about 20 minutes time. So now we are going to move on to the tools and applications. So here you're going to hear a brief talk from each of the projects about this subject. And I believe we are starting with MYRIAD, please.
Yeah, thank you very much. So I've got 5 minutes now to try to describe some of the tools and approaches coming out of MYRIAD. Of course, I certainly cannot describe them all, but this is an introduction to some, and I will be very happy after this event also to continue any discussions with anybody. So as I said, MYRIAD is about trying to enhance, to shift us more towards this multi-risk thinking, both in terms of how we assess risk, but also how we try to manage risk. Next slide, please. At the heart of the project, we developed a rather simple, actually, framework. And this was a framework which is basically a set of 6 different steps that could be taken to carry out a multi-hazard, multi-risk assessment, and also to try to develop a plan of how to reduce that risk for the future. Now, what we didn't do in the project is try to develop one tool or model which would be able to, look at all kinds of interactions and give you some probabilistic estimate of risk in all locations around Europe. Simply because we understand that there is so much, it's so context specific to the region that's been looking at, the scale, the kind of user, that we didn't feel that this was an appropriate methodology. But rather, these are 6 very high-level steps to be taken. And then we provide so-called guidance protocols for each of these steps, which are basically some questions to be answered. For example, in finding a system definition, how to do that. And it points the user to different tools, methodologies, examples of how this has been done, both within the MYRIAD project, but also in other projects, for example, the brother and sister projects here, but more widely. And next slide, please. The idea was basically to co-develop this framework, so these 6 simple steps together with our pilots. So we came up with this initial framework at the start of the project, some 4 years ago nearly, and through a series of 4 different workshops with our stakeholders, we have iteratively updated this framework over time. But what's the framework supposed to do? Well, it actually helps us to develop this, what we call a forward-looking disaster risk management pathway. So, for example, in the Canary Islands, what we did was set out and look for a sustainability challenge in the region, which really is central to addressing a lot of the issues in the region. So, for example, the Canary Islands is a lot of the GDP comes from tourism. It's also has many different kinds of hazards going on. So one of the questions that we asked was, how can these kinds of island regions with this strong dependence on tourism become more resilient to multi-hazard risk? And then we work together with a range of different sectors within each of these pilots, which need to talk together to be able to reduce this risk. So in this case, obviously, tourism is one of those, but also food and agriculture. So a lot of the food is actually imported because also to support that large tourism industry. And a lot of energy is also needed, again, partially because of this large tourism influx. So what we try to do is work together to develop a plan for the future that brings together these 2 different sectors and then looks at all of the different hazards involved and those different interactions, such as Rui just described. So it's quite different to a traditional risk assessment where we may say, well, what's what's the risk to flood in some region, and what measures could we take to reduce the flood risk? No, we start at the future and then try to work back and design pathways to get to a desired outcome. Next slide, please. I'm just going to quickly go through one of the more technical tools of the project. So that last one was more conceptual. This is a method developed by Judith Claassen, basically to develop a global multi-hazard event set. So where do we know, can we map in the past where these different multi-hazards have occurred? This is a global study, but within MIRACA, so there's already a link. We've actually been working with colleagues there to do this also at the European scale, using more high-resolution data. Next slide, please. So, well, as we've been talking, there's lots of different kinds of hazards. Next slide, please. And what we wanted to know in this with this tool is, well, can we actually start to map where they come together in space and time? So where do we see those overlaps? Next slide, please. And you can, yeah, there we are. And basically what we did is we took existing data sets of single hazards, so floods, droughts, earthquakes, volcanoes, wind, and so forth, where we have a spatial footprint, hazard footprint of where did it take place in the past. And we also have information of how long did it take place. So when did the flood start? When did it end? And so forth. Next slide, please. And then I'm not going to go through all the details here, but we basically developed an algorithm then that looks at when is there both spatial and or temporal overlap between these different single hazards, and that we can then class these as one set of these multi-hazard events that Rui was talking about. Next slide, please. And then we can really start, again, without going into details here, these are different regions. We can start to map what kinds of different hazard pairs or groups of different hazards have we seen that occur frequently in the past. Next slide, please. And then here we can start to map those hotspots here at the global scale of this multi-hazard. But as I said, this has also been carried out now in Europe at the European scale. Next slide, please. And almost wrapping up now, but this is some software which is coming soon within the next month or two. We're actually developing open source software where you will be able to click on any of these NUTS2 regions within Europe and then try to actually get the different scenarios of different plausible kinds of events that could occur together, and then get an estimate of the risk using different metrics depending on which sector you are involved in. And then I think it's the final slide, please. Yeah, this is one other tool that we've developed. This is a disaster risk gateway, and what is that? Basically, it's a wiki. It's a wiki portal. So what it means is that anybody, also anybody in this discussion here, can go online and add to this wiki. And what we have basically are some definitions related to multi-hazard risk, similar to those that were already described. But we also have a catalog of different tools, different approaches that one could use for assessing multi-hazard risk. Some of it's been filled in by MYRIAD tools, but also tools that we know of from other projects. But I would also invite anybody to, well, both look at this tool, but also if you have your own tools and methods to share them on this platform. And for now, that brings me to the end of this presentation. Thank you.
Philip, thank you. That was really interesting. And I would encourage any of you to take Philip's offer up there and see what MYRIAD are doing and some of the tools that they've got integrated. There's some really helpful stuff there for whatever part of stakeholder group you fall into. But you're not here to listen to me, so I'm going to hand straight over to MEDiate, if you don't mind.
Thank you, Ben. Yes, so I'm Chen Huang from NASA. We are the coordinator of the MEDiate Project. And the key feature of the final solution of the MEDiate framework, first is enhancing the multi-hazard and cascading impact understanding. So for the local community and practitioner, they improve their knowledge about multi-hazard and cascading impact. The second one is developing risk and resilience framework. So the current framework, mostly the applied, is focusing on risk, a single component, where we emphasize on the resilience, particularly related to the critical infrastructure and how we can improve the management in terms of risk and resilience together. The third point is supporting multi-criteria decision-making. As many other studies, we propose other metrics that is non-monetary. So we're focusing not just saving cost, but also saving lives, as well as other possible social impact on the some social functionality and services. Last but not least, we're providing tools for visualizing and as well as analyzing disaster risk. And it is all integrated in the web-based MEDiate platform. And next slide. Here we try to go through components like all the features I just mentioned one by one to show you and some example. How we improve this understanding of multi-hazard interaction and cascade impact. So we have the framework and we got also the project in the conceptual graph. First about the scenario with this map. What could happen in the local and what is the current exposure to possible different hazards. For the given scenario, we're looking closely into what hazard can interact with each other. That is the lower right corner. And then we highlight in red boxes what other X factor can make situation worse. And the green boxes is what mitigation action we can do to address the intensity, scope, or frequency of this hazard. Last but not least, we have the impact chain. So zoom out to look into cross-sectoral impact from different scenarios. Next slide. Then we propose this new disaster risk and resilience management framework. We in the middle, in the center of this framework is the risk and resilience assessment in the darker blue. And we propose to test different risk mitigation and resilience enhancing strategy throughout this framework. Now I'm gonna zoom into the middle of this framework. In the next slide. Conceptually, we have a key component in the assessment framework. That is the exposure, hazard, physical and social vulnerability, risk and resilience metric. And all these are for the final use is selecting the optimal risk mitigation and resilience enhancing strategy. Another key component is we're looking into a different timeline. So we are not just looking at the current exposure hazard, but also what could happen in the future and the dynamic changing in the vulnerability and the metric to measure them. Next slide. When we're looking at the exposure, we classically have the physical environment and people, as well as social and economic infrastructure. Here, as I just mentioned, we are both looking at the current and the future projection, what could happen in our society. And the next we are looking at the hazards. For the current practice, many stakeholders we've been talked to in our pilot sites, they have what they consider as a multi-hazard map, but it actually is a multi-layer single hazard. And our added value to them is identify what is the interaction type between different layers of single hazard. And that also helped them to identify what could happen, and not just on the single hazard, but multi-hazard scope. On the next slide. We now dive into the vulnerability. We have the hazard can occur as the flood in this blue polygon, and it impacts the infrastructure, for example, the hospital, the housing, and the governmental capacity. And all these can also have significant impact on our socio-economic response to all this disaster. So these provide some static but also dynamic transform through the time picture of the coping capacity. On the next slide. Next, we are looking into, given this possible impact, how do we measure, which measure should we use to find the optimal mitigation strategy? Here we propose not just the three, but as shown here, we look into economic metric, social metric, and environmental metric. Of course, there's more metric as multiple project has developed new metrics to describe this. But given this example, we go into the next slide. We ask the local stakeholder to say, what is your preference? What is your priority in line with your operation work? And then we choose the metrics that are relevant and reflecting their priority in the decision-making process. So stakeholders select the risk and resilience metric and given their weights for strategy evaluation. And these are all the input for the decision metric. In the next slide. So as shown in the flowchart from the left, we have the scenario given multi-hazard. We have information about the possible risk and cascading impact using different metrics to describe to measure this. Then we have the stakeholder group to evaluate the system dynamic across different organizations, actors, and sectors, and using a serial scheme where we, in our context, is prioritizing what is the high priority criteria to consider within their decision-making process. In the end, all this input come into the strategy analysis. We provide a graphical and an interactive map to help them to understand what is the optimal option given the scenario and their priority. And this also help them to explain their mitigation strategy to the general public, make the process more transparent. The final, next slide. We have integrated all the information I just mentioned before, the methodology, the data, as well as the stakeholder input into the MEDiate platform. The platform is allowed different stakeholder groups to work together to manage disaster risk, consider multi-interacting hazard and cascading impact. And you will need various digital layers that you already have, and the added value will provide us, as I just mentioned before, the improved enhancing and new metric and decision making and the platform. With this platform and general media framework, we tested in different pilot sites. In the next slide, we have SS is one of our pilot sites, and their focus is on how to integrate the risk and resilience management with the innovative research development to their local community and operation authorities. Here are some workshops snapshot. And then on the next slide, we have the Oslo pilot site. Oslo pilot site focusing on improving crisis management through knowledge empowerment. So all the methodology we provided first conceptually and to them, and then they will ask themselves how to adapt it. And we have this different workshop to discuss possibility in the future. The next pilot site is in Múlatein, Iceland. It is a really small community, but it has a really strong focus on resilience enhancing for a local community as a topic. And so here again, we show some workshop snapshot and then some activity planned out during the project. Last workshop or testbed is the NEAS. The NEAS testbed focusing on improving multi-hazard and multi-risk disaster management. And here we also show some workshop and serious game screenshot. And with this, we almost conclude the MEDiate project and wish you to join us in the following workshop in the SRE of this webpage. Thank you.
Shen, thank you very much. Again, really interesting. And I think it really highlights that what risk means is different to multiple different stakeholders. So what I may see as a risk in my work or personal life, somebody else won't, or they'll see a totally separate risk. So it really shows just how diverse and interesting the subject is. So Shen, thank you for that. If anyone's got any questions, please put them in the chat and we will come back to them. But now I'm going to hand back to Rui for C2IMPRESS, please, sir.
Hello again. Okay. So now speaking specifically about C2IMPRESS, now in a few minutes, I already spoke quite generally about the generic concepts. So here, one of the key tenets of the whole project to improve this understanding and the action that can be done relative to the multi-hazard risk cycle and how to actually deal with it on the fields to strengthen the resilience of our societies. The first thing that we tried to deal with was with this very key problem is, wait a minute, we have so much happening, so many different places, every place is different, every person is different, every species, everything. So it's like looking at molecules in a fluid and say, oh, wait a minute, each one has their own specific dynamics. How do we encapsulate that into a macro-physical world without losing crucial information relevant to local variables, to local people, to local lives, to our individual trajectories, whilst keeping coherence? This is through foundational principles, like we do in thermodynamics. You know, it doesn't matter where I am in the world. It doesn't matter where I am in the universe. You know, the first fundamental principles, many of which nobody knows yet, these are universal. These are cross-cutting. So what we did here is trying to find, you know, the fundamental principles, some of them pertaining to multi-hazards. Next, please. Next slide, please. Okay, so in order to do so, rather than attempting to model everything everywhere in a classical manner, which would require, for instance, numerical modeling, is making lots of assumptions you know, typical numerical models, they work locally. You know, for instance, Navier-Stokes equations, they are very local. But if you try to integrate globally, you will get something that is actually not representative of the whole diversity of the behavior of a fluid. With people, it's even worse because we have our own agent, we have free will. And so life is much richer. Our society is much more complex in how it interacts. So the purpose here was to create an interdisciplinary framework that rather than giving you the numbers only, because you can't just guess the numbers in 100 years about how climate is going to change and how people are going to behave, but providing the protocols, the foundations, the tools that allow you to build for each specific case, for each specific region, your own models, but with a common principle-based system of systems. So this is what brings everything together, not giving the numbers, not saying, I'm going to, you know, this is going to be the rain in 100. No. Nobody can say that. It's about how we can work together towards designing our models and having a framework to do so. So we have partners that so Artilia developed a public-private civic partnership to essentially bring the people together, stakeholders together of different sensitivities that have different perceptions of our world, to work together to try to figure out such principles at their local scales. At the same time, we developed the aggregative system of systems that I mentioned before. And then you have the real-time forecasting and rule-running systems that leverage the local knowledge, but also the physiographic information and this system dynamic modeling, where you have not certain numbers, but actually distributions of distributions that essentially assess a thing that is usually missing a lot, which is the full encompassment of the fact that models not only have uncertainty built within in stochastic elements, but you have unknown unknowns, the fact that we can never know everything. And it is important to convey that notion to decision makers, because they think, oh, I have a downscaling of 5 kilometers here. No, it is highly uncertain. Being aware of the uncertainties, being aware that climate projections are magical thinking. What we did as well, and we did so for the project, we did climate simulations, we did Earth system dynamic simulations for plenty of variables, natural, social, technical, everything on the soil, on the atmosphere, on the ocean. But it's important, and that we developed that in the project with the human behavioral models, with novel integrated multi-hazard frameworks, with use of social media analytics, all of this together to raise the importance that the future is in our hands, notwithstanding all the mathematics, all the physics that would do things if we would not be in the equation. Next, please. Next, please. Next slide. Okay. So what is done here is then going from these foundational principles to actually developing breakthroughs, real-world impacts, things that operate already on the field in different pilot areas and beyond. So, doing a disaster crisis for risk assessments and doing work for preparedness, following the risk, the civil protection cycle. Be prepared, see what is going on, detecting the challenges, detecting the threats, thinking how they are working together. And then, okay, preparing then, anticipate, simulating. Okay, now let's prepare the response. Responding. But then also always thinking about recovery. How we rebuild, how we build resilience. Resilience is not about avoiding the disaster. It's about being able to rebuild and restore your system in a fully functioning manner after disaster strikes. And then working towards that to strengthen resilience, to do so in an interdisciplinary, interactive manner across stakeholders of different areas that have different skill sets, and that we then bring together into the system of systems, and then communicating in a way that is in the different audiences perceived and uptaken in the real world rather than being put on the shelf. Next, please. Next, please. Okay, so just an example here to keep things short. So aside from also looking into the early warning systems for the different hazards and multi-hazards happening at event scale, for civil protection, for responsiveness and so on in a very clear operational manner, it's also important to study, to assess, to look into what might happen, not only in terms of climatic variables, because you have plenty of projections doing that with all different kind of scenarios, some more realistic, some completely, in a fantasy world, but very important to also compute, determine, and think about possibilities of how the hazards might interact in future conditions under not only Earth system dynamic geophysical settings, but also in terms of the socioeconomic and the human behavioral and all these social dynamics that completely changes how our planet might look in a few years. And doing this kind of assessment and also helping design adaptation, mitigation, long-term territorial planning. Civil protection is intimately tied to territorial management. And thinking of that and sitting together and working together is a core tenet of the project. Rigorous mathematics is important, and at the same time, a rigorous and deep solidary work together with the colleagues on the field. Next, please. And this is the last slide. So very core to C2IMPRESS is seeing beyond the data, not relying on the fact that the past will represent the future. The past is important. Learning from the past, very important. Past lessons, lessons learned. You manage the present with the past, okay. But to plan the future, you need to look far beyond. You need to look at tools, methods, and talk to the people that have the vision our people in the field that have the vision to see beyond what has been in the past records, to see signatures of potential emerging behavior. Here in this case, for instance, precipitation, long-term precipitation predictability. We have been making hindcasts for validating information pertaining to precipitation dynamics, especially extremes. If you look at recurrent machine learning artificial intelligence techniques, they will find certain patterns, areas where you see on the left, areas that are recurrent, where you have either recurrent drought or recurrent excess precipitation. They're all good. But if you have surprises, if you have regime changes, if you have unprecedented, non-periodic, chaotic flows, as you have most of the world, then you need something beyond. Earth System Dynamic Intelligence, introduced and further developed in the scope of the project, allowing us to see beyond, not just by running a weather model, but running an Earth System novel, Earth System Dynamic Intelligence, where we have the flexibility to admit the variability of people's behaviors, while at the same time abiding to fundamental physical principles, some of which were unveiled during the project, but many more are yet to come. The journey is just beginning. Join us and let's have a discussion. Thank you very much. Goodbye.
Rui, thank you very much. Some really good stuff in there. I took particular notice to the sort of human behavior studies and what that means in the real world. I think we quite often overlook human behavior when we talk about disaster and disaster risk, but obviously that is the real reason that all these projects are ongoing and we're doing it. So finding that balance between policy research and engaging with people on the ground is key to getting people to listen and engage and make this work more impactful. So that was great. Thank you very much. Any questions, again, please put in the chat or stick your hand up in 5-10 minutes or so when we go to the Q&A. But now I'm going to hand over to Dr. 𝒂𝒂𝒔𝒕𝒆𝒓, if you don't mind, sir.
Yeah, thank you. So yeah, I'll talk about the MIRACA project in great detail over here in the 5 minutes that I have. As I said, it's called Multi-Hazard Infrastructure Risk Assessment on Climate Adaptation. Can I go to the next slide, please? So the goal of the project is essentially to develop a comprehensive understanding of critical infrastructures like energy, transport, telecommunication networks, how these infrastructures are affected by natural hazards, what are the risks to them, and then how can we propose methods to enhance their resilience. Next slide, please. And this goal and objective is kind of, finally, it'll result in 3 key outputs. One is to understand, create a guidance on technical and economic appraisal of adaptation strategies. So considering what network adaptation strategies we can use for infrastructures and what are the trade-offs when we think about investing one infrastructure at one location over the other because of limited budgets and limited resources. The second output is a technical workbench. We have 5 use cases. I'll briefly speak about them in later slides. But essentially, we have use cases that show the potential of our methods, which are being created at the European scale. But what we want to also give out is tools and models that as we develop, we want to give them out openly through these Jupyter notebooks, which is in a Python programming language, in case you're not aware of what Python is. And then these tools essentially explain our methodology and its usability for any technical user. Then another output that we have is essentially the creation of an online interactive viewer. And this viewer, as you can see over here, this is a mock-up of the viewer. It's still being developed, and it'll be developed, a first prototype, by the end of the year. So the viewer will showcase what are the most important risk hotspots within Europe of infrastructure networks. And it will also kind of have a bit of a scrolly telling approach, which we have which we're adopting in MIRACA to understand, like, if there's an event, what happens in the event, what infrastructures, where they're affected, and what are the cascading effects of those disruptions. And then you can inquire that and look at the whole chain of kind of disaster and impact and the adaptation options and benefits. So we are trying to develop this for the whole pan-European scale and try to also look at current and future hazards. We are relying on hazard data sets from projects like MYRIAD and other kind of sister projects in Europe who do much better job in creating hazard information. We are more concerned on what happens when these hazards create an impact on infrastructures and the network cascading effects that emanate from them. Next slide, please. So we need MIRACA that we feel, maybe that's why we got funded. We need it because we need to enable this action to catalyze adaptation into critical infrastructure protection. Critical infrastructure protection is something, generally we think of adaptation and investment in protection against hazards is generally done at the building, household, those kind of levels. Infrastructure protection generally is less understood. So we believe that to enable that action, a project like MIRACA is needed. We need a systemic risk approach that is kind of generalizable, widely pan-European scale, but then it has elements of local knowledge and local understanding, and it needs to be kind of incorporated into the climate adaptation appraisal and critical investment decision process. Then we also need to understand adaptation beyond a simple asset level understanding, where we look at an individual road or a bridge and see that it's flooded or affected by any other hazard. We need to look at what happens beyond this. What is the whole chain of kind of people, businesses, other infrastructures, and interdependent cascading effects happening, and that will give us more understanding of indirect losses, the opportunity and the costs, and the co-benefits that will come along with undertaking adaptation. Next slide, please. So this slide, I'm not going to go into detail, but this shows our framework. Essentially, it's kind of that we are developing with colleagues and partners across 6-7 universities in the consortium. But this approach is looking at single or multiple hazards, integrating them with infrastructure details, spatial asset data sets to understand exposure and vulnerability. Other projects, sister projects have also discussed this. The key component, what you see over here in the third kind of block over here, the disruption management, which is essentially the whole network cascading effects. This is what we are really kind of focusing on, understanding that if your road network is disrupted, how does that cascade to even the rail, the ports, the airports, and other interconnected multimodal networks? If electricity is disrupted, how does it affect telecoms? How does it affect transport systems? How does it affect schools, hospitals, and so on and so forth? And this also further goes into the last, which is block, which is the thing at the very bottom, the systemic risk framework, which looks into wider macroeconomic impacts. And this will then help us build this whole kind of detailed understanding, which can then feed into an adaptation appraisal project process. And we are building these decision support toolkits and communicating and disseminating our findings with stakeholders that we have in different use cases. And this is what kind of would help us create an interactive project and for use of wider audience. Next slide, please. So the use cases which I kind of alluded to, one of them is pan-European, is the TEN-T corridor network. We are in conversations with DG Move, who manage and operate this network. Then there are more kind of national scale case studies. Spain, looking at droughts and wildfires and heat waves in the Catalonia region and their effects on road connectivity to tourism and other kind of areas. Looking in the Netherlands, working with stakeholders in the Netherlands who are interested in telecoms and electricity networks and their interdependencies and how these are affected by floods, heat waves, and storms. In Greece, we are working with colleagues who are looking at schools and hospitals and how they are affected by earthquakes, floods, and landslides. In Slovenia, we are looking at the national scale transmission and distribution energy grid of Slovenia and how that is affected by floods and landslides and how that affects the usage of energy in the country in terms of the businesses, the people, the industries, and households who use them. And in the pan-European, just coming back to, we're looking at the droughts, floods, and storms. How do they affect the whole multimodal TEN-T corridors that pretty much are the lifelines of the European continent? Next slide, please. So yeah, just I went through the project partners. These are our partners. I'll not go to the slide again. Can we go to the next slide, please? So just to conclude, the few lessons that we want to learn through this project is that we want to go beyond asset level impacts, understanding end users and how they will benefit from a system level approach, which is more complex and more complicated, but we want to convey that that's the value of doing that, especially when we think of infrastructures. Infrastructures never have localized impacts. They have cascading wider impacts. So we want to think about climate resilience to go hand in hand with other transformations that we talk about net zero and kind of mitigation, but we want to also integrate resilience and adaptation into the decision-making process. And we want to convey this message that essentially the data and the knowledge that we create should help kind of overcome a technical implementation gap, and that will help a governance as well that goes into making decisions on climate adaptation. Next slide, please. This is our kind of just tools website and everything that you can follow our project. Thank you very much for listening.
Dr. Raghab, thank you very much. Really interesting, and obviously a lot of work to do around infrastructure effect on disaster. We had a fairly recent example of it in the UK with the fire that managed to take out Heathrow Airport for 2 days. Something that seemed fairly small and innocuous obviously had a worldwide effect. So really interesting stuff. Thank you. Excellent. Right, we are going to move on to the panel discussion. I'd just like to introduce MEDiate's coordinator, 𝑹𝒊𝒔𝒂𝒂𝒓. Abdel, are you able to say hello quickly?
Yeah, sorry, I'm a bit late. So, yeah, my name is 𝒊𝒔𝒂𝒂𝒓. I am a principal research engineer at NOSA. NOSA is a research foundation in geoscience. And I'm coordinating MEDiate with 18 partners from 7 European countries. And MEDiate, for those who don't know, it's basically a sister project of Paratus. We belong to the same call, which is about enhancing disaster risk management governance. Yeah, thank you.
That's perfect. Thank you. So yeah, please feel free to join in with this panel discussion. So Rui, I'm going to come straight to you before we go to the whole group, because there was a question in the chat for you. The questions come from Maria, and it was, is it possible to understand feedback loops in SOS from the land cover change? How does this force the risks to higher level?
Hi, Maria. Thank you very much for your question. Very pertinent question. So SOS means you are meaning the system of systems for multi-hazard risk intelligence networks that I was presenting early on. So indeed, this use case is indeed one of the aspects that is contemplated in the tool. Why? Because unlike traditional modeling approaches where you would, let's say, treat the water cycle, you rain, and then you go down the catchment, and you go to the sea, and evaporates, and goes back, and so on and so forth. Here, the feedback loops are not only cycles, but actually, and most realistically, highly entangled nonlinear interplays. What does it mean? It means that, an example, when you have something happening to the land, and this is why our forecasts, even in the short range, are more meaningful in that regard, but especially so in the longer term where land cover is changing more. The fact is that what you do to the land affects the weather, not just the climate in the future, but affects the weather. You have, let's say, you have a big flood happening and so on, it covers the entire agricultural land. And you think, okay, this was an impact of a big storm, and then you had high soil moisture, and then you had a lot of other features that prevented infiltration. It was saturated. You probably had a previous event that impeded such. But when you change what is on the land interface to the atmosphere, you inherently change the weather regime. So while a traditional weather forecast will not be looking immediately at what is happening to the ground at real time, definitely not, because the land cover mask in Earth system models is updated not so regularly, so it's with a longer latency. Here we have spaceborne sensing that permanently in real time, 0.06 seconds, is always capturing what is happening to the land. So you have a landslide, it will change how the micrometeorology happens. You have crop, I was now collecting hay. I was chopping the grass. That will change local micrometeorology. Of course, it will not create a hurricane far away. Why not? Because then you have dissipation of these perturbations that fortunately in a dissipative world, you will mitigate these effects over long distances. But you do have, especially when the land cover is critical enough, it will indeed trigger effects that can then percolate across scales, upscaling, and then changing weather regimes, and eventually also changing climatic patterns. That has been happening. You see that a lot, and this needs to be incorporated in the models. In some Earth system models, you do have that effect in multiple scales that are broader, so interannual, but in the local event scale, usually you would not find that, but the system of systems for multi-hazard risk intelligence networks indeed captures those feedbacks so that we can then feed this updated information, because what happens in the air is crucially affected by what happens on the ground. Everybody knows that, but it was indeed not present in state-of-the-art models in such a representative manner. It was usually treated with parameterizations that were approximations, averaged states of the land cover. No, it's not actually not just the land cover, but the health of the plants and the health of the soil and what happens also beneath the soil. You know, the soil moisture content, not just at the surface, but also to a few centimeters further in. That also influences the weather. And this feedback is indeed contemplated and is a crucial element of added value relative to the state of the art. I hope that this answered your question. At your disposal for further discussions in more detail.
Thank you, Rui. Maria, thanks for the question. I love your background, Maria. It must be cold up in space, but it looks very smart. I'm going to stop sharing the screen just so everybody can see each other properly. We'll go back to it for the end of the presentation. It also, Rui, you've suddenly appeared very big on my screen. That's scary.
Ooh, scary. Oh, no,
also
I'm not
allows
scary.
me to see if anyone's got any questions. Before I go up, we had a couple of questions sent to us prior to this webinar, but before I move on to those, does anybody else have any questions for the panelists? Looking for any hands up? No problem. Okay, great. So this is a question for all of you then, please. So what do you think are the main challenges in operational transfer from frontier scientific advances to everyday end user uptake? And how can we ensure that all of these tools are actually used in practice in real life? And that is to all of you. So if any of you would like to answer, please fire away.
I mean, I can say some words from the MYRIAD project. I think this is, of course, always quite a challenge. I think the way that we tried to address this in MYRIAD was really from the get-go, right? Actually, during the writing of the proposal, that we already brought in from the 6 sectors who we were working with. So that was tourism, energy, agriculture, wetlands, and so on. There were 6. We brought in representatives of each of these different sectors to already at that phase actually start to understand what type of information is actually required in those different sectors. And then within the pilot, so those 4-year pilots that I was talking about, we did the same to actually start first understand what are the kind of so I'll give an example. So we started off developing this software tool, which the idea is that you would be able to use it any location in Europe to kind of get an assessment of the risk, right? But then we spent a lot of time speaking, engaging with many stakeholders in the region to say, okay, but what indicators, metrics of risk do you actually need? So, we really started to do that engagement from the get-go. I think something that it takes a long time. Also, so you need to build these good relationships, the trust between the science partners and, let's say, more practice and policy. And I think for me, an important aspect here would be ensuring the longevity of some of these collaborations that we have, right? So that at the end of each project, you don't basically stop that collaboration. It goes into a nice report, and then you pick up a new project with new partners. Of course, that's very nice, but having these kinds of exchanges like through this cluster where you can keep some of those collaborations going, I think that's important. It means that you can really let's say, start running in the next project. So I think that would be one point.
That's great, Philip. Really interesting. Anything else on that from any of our other panelists?
Yeah,
I don't know if anybody.
sorry.
Okay. Go ahead.
Yeah, thank you. If I can add from the MIRACA project perspective, so we have kind of, essentially we're looking at infrastructures, and most of our stakeholders are infrastructure owners and operators. And for them, one of the challenges is, first of all, and they might have very good knowledge of their own infrastructures. They don't have much knowledge about what's happening beyond their system. So that's one of the challenges that they face. And they've been very kind of keen to understand that, these whole interdependencies and cascading effects. It's a bit of a challenge to convey that, because kind of that's a very technical kind of complex problem in itself. So kind of how do you convey that has been a challenge for us as well. So interacting with them, understanding their perspective and kind of what knowledge and systems they have. One of the things is, like, these organizations sometimes have their own knowledge and systems and their own data sets and everything that they want you to work around, which kind of is, if you're doing multiple type of use cases with different stakeholders, you end up with different kind of things. And how do you distill that into one decision-making tool that you want everybody to use? So that's a bit of a challenge, and we are learning through that ourselves as well, to be honest. And it kind of helps us also to kind of understand that what science we produce, and sometimes we think we have a very fancy, flashy kind of thing that everybody will be impressed by. It helps us kind of reevaluate that as well. So it's been a kind of interesting process of co-creation for us, which is kind of, it's still evolving. We are kind of still, our project ends by the end of next year. So we're still kind of in the middle of our project at present. So some of these tools are going to develop in the next few months. And we are trying to interact with them during the whole development phase, like showing them initial prototypes, saying, do you like it? What do you think? Does it convey the message that is relevant to your needs? That's kind of very important. And kind of for them to use it, one of the important things kind of we realize we need definitely some engaged stakeholders, some stakeholder champions who kind of want to really engage with us. So we have been persistent sometimes in the European bureaucracy. You kind of send emails and it takes weeks and months to kind of get feedback. But once we have found a person, we're trying to kind of stick to them and kind of ask them, like, to provide, and they've been quite helpful and quite useful for us. So yeah, it's kind of essentially interactive co-creation, which is very important for us. Thanks.
That's great. Thanks, Rega. 𝑹𝒊𝒔𝒂𝒂𝒂𝒂𝒂𝒂, you've got your hand up.
Yeah, but maybe Rui was first. Yeah, he can start and then it's me.
Okay. Thanks. So essentially, as was already said before, the way to make this bridge is making things in a way, developing the science, the frontier science, natural, social, technical, in a way that doesn't even require a bridge. And how do you do that? So what we have been doing, and also other projects here in the room, is exactly the co-creation. You sit together, you are on the field, you feel it, you sit together already there where things really happen, you get immersed. So when he sits in an academic ivory tower, so if I sit at university and teaching to my students, I always take them to the field. Why? Even if it's geometry, differential geometry, mathematics. Why? Because when you sit on the field, when you go to actually where things happen, where nature and society play around in the complex system dynamics, and you talk to the people that really feel the impact, and you are one of them. When you live that, and when you really co-create and develop and discuss early on from day zero, not even day one, day zero, before even starting, and you are there developing that science, you have the technical skill. Others may not. But if you are sitting together, brainstorming together, creating, co-creating, co-evolving the science together, the final science will not be detached from the real world, will not be detached from the end user. It will be something deeply intertwined. It will be something co-evolutionary. And then the people, even if they don't know the math and physics and the system dynamics and so on, they will feel it because they were there with you as you were building it. So, and then it's by entanglement, co-creative system dynamics, being there ourselves, not being afraid to develop it together, not being afraid to try to speak with different languages. If we develop the language together, we can do it, and at the end, we don't need a bridge because we are already there. This is what I wanted to say. And of course, agreeing with what all the colleagues were saying, because we are all in the same boat. Thank you very much.
That's great. Thanks, Rui.
Yes. So from MEDiate perspective, you know, there has been so many tools, very interesting tools that has been developed in previous programs, like for example in Horizon 2020, FP7, and those tools actually they are quite state of the art. Within Horizon Europe, we didn't really develop a lot of things that makes it very different from what has been previously developed. But the main difference for which those tools are all in archive and have not been adapted is because the potential user and the stakeholders during the development of those tools have been getting involved as object to be tested, not as a partner. As a consequences, we have developed tools that use very different language than the language that they use. It does not take into account their protocols, the way how they work. It doesn't fit their system. It doesn't fit their philosophy or the way how they communicate, how they interact between them, between those different stakeholders. And this was the big challenge for which all the solutions end up in archive and not being adapted. I think for now, with the Horizon Europe, I think this is also has been clearly understood in the European Commission, where in New Horizon Europe program, it becomes mandatory to engage your end user, potential user, as a partner, so that there is a success. When you finish your project, it somehow went to the next stage, which is taken up or integrated. And this is why in MEDiate, as well as in Paratus and MYRIAD, other projects, they have the end users, different group of end users as a partner. I think we start to understand each other. We are developing a solution that fits their system, not replace their system, but be like complementary to what they have as a system. We use their language, we use their protocol. I think now the coming challenge, at least from what we learned from our end user partners from Oslo, from Essex, is there is still a lack of a legal responsibility, because the tool we develop, it can be used by different stakeholders. Different stakeholders use different data, they have different protocols, and to share this data between them, they need legal responsibility, they need a framework, policy. And this is the challenge now that we are trying to work on. And next, in order to the solution that we are developing, it can be integrated. First, you define the responsibility, then the legal responsibility, then they can share the data, they can work together. Thank you.
That's great. Really good points. And a lot of what you said really points towards the what we hope is the future of the disaster risk stakeholder hub going forward. So yeah, thanks, 𝑹𝒊𝒔𝒂𝒂𝒂𝒂. Maria, you've got your hands up.
Yeah, hello everyone. Thanks for a very interesting presentation and talks. Just a few comments that right now, for example, during the project, means facing the other difficulties already mentioned here, but still in some not so well developed economies and countries, stakeholders are limited in their legacy. I mean that they cannot enter as a full consortia part because they do not have mechanism how to, consume the budget, how to consume the EU budget for their own needs, for example, to encourage their own employees. And so this is a great obstacle indeed, because like in well-developed countries, the mechanisms are clear, but for example, in Eastern Europe, this is a great deal how to attract end user and stakeholders because they do not have the pathway how to consume this money. Yeah, that's it.
Maria, that is a really good point. And it is obviously different for each region and each country.
Yes. Yeah, this is true. Yeah, we have experienced it. Yeah,
absolutely. And I'm aware this was an ongoing conversation at the SMIG event this year, that how do we actually actively engage end users in all these different circumstances, and each country, each region's got a really different answer. Some best engaging end users, citizens through their responder organisations. Other countries, other areas don't trust their responder organisations to do that. So it is, you're quite right, it is a real battle, and one we will continue to have, but continue to work towards, I would hope to think. Great, we've only got 4 minutes left. So before I close us down, is there any closing statements or anything anyone would like to add?
Just a 10-second note here about this last point, which is very relevant, is exactly why, when he was saying, this is exactly why, with or without partnership, with or without formal membership in a consortium, it is important, as I was saying before, from day zero, even before day one, that we all sit together and that we do our academics from the field, that we are there, that we feel all and develop all together. So it is in C2IMPRESS, we also have the end users as part of the consortium as equals, developing from day zero. But even if it is not possible, it is crucial that with or without EU money and with or without that we always keep in touch, and a very good relationship, as Philip was saying earlier on as well, always working together, not waiting until we have the tool, but before we build it, we sit together and we think together how to build it together. That's the spirit of co-creation. And this is what I would like to leave here, is that we are building the future together. And that's what you should always be doing, together. Scientists, practitioners, we are all part of the same society. Let's work together. Only then we will be able to synergistically achieve our shared future and shape a better world. Thank you very much. This is what I wanted to say for now.
Thanks, Rui. Really good point. And I answered your point from a responder point of view. Is those relationships are invaluable, because I know I've worked on projects purely from a response point of view. And the research and innovation is so far ahead of what we're seeing on the ground, if you like, that you can really easily become disengaged from it all. So creating that constant feed so that you see the outcomes and see it in practice, even if it's 5-10 years down the line, is really important to engaging new people from the start. So really good point. Thank you very much. Anything from anyone else?
Yeah, I wanted to thank all the presenters for this deep dive into the multi-hazard risk assessment work, and just a thought about the collaboration spirit that we're talking about. I wonder whether this type of collaboration opportunities among projects that work with similar topics can also be extended to, I don't know, integration of tools and the disaster risk stakeholder app. So I think this is it was great to hear from different perspectives about this topic. And that's it. I wanted to say to the participants that the next webinar is going to be after the summer break. So to stay tuned and have a wonderful summer, and see you soon. Thank you, Ben. That's it from my side.
Thanks, Sonia. Yeah, and that's all I've got to add really is a huge thank you to presenters, panelists, and those of you that have joined us and asked questions and engaged today. Some really, really interesting conversations that I'm sure we will all take forward probably for many years to come yet, if all goes to plan. This webinar will be uploaded to the DRS Hub by this evening. So please, I will share the link with you, but please do share it with colleagues or anyone else you may think will be interested. And we will also send out a feedback form. So please fill that in. Anything positive, negative, too long, too short, too PowerPointy, anything is really helpful. We're in the early stages of building this up, so you can't be too critical. So please do. That's it. I will leave you all in peace. Thank you all so much. And hopefully see you all again very soon.